Okay, so number one on the review sheet here, we have find the inner product of these two vectors. So we're going to take, let's see, this is number one, we have u, 1, negative 5, 0, 7, 8, and v, negative 2, 3, 3, negative 1, and 1. And we want to take their dot product, or their inner product. So that just means multiplying all the corresponding entries and adding them all up. We want to remember we get a number at the end of this, not another vector. So we're just going to have a negative 2 from there. Negative 5 times 3 is negative 15. 0 times 3 is 0, so we're not adding anything there. Then we get a negative 7, and then 8 times 1 is 8. And if we add all those numbers up, let's see, 1, this should be minus 16. So that we have the inner product is minus 16. Number 2. Wrong sheet. Number 2, normalize each of the following vectors. So for our first vector here, v is 3, 2, 1. So to normalize the vector, we need to divide it by its magnitude. So the first step is going to be, so for part A, first step is going to be to find the magnitude of this vector. So that's going to be the square root of 3 squared plus 2 squared plus 1 squared. So that's the square root of 14. So then let's call this vector u. So the v vector we started with, 3, 2, 1, normalized is going to be 3, 2, 1 divided by the square root of 14. And we can actually divide each of those components, and we get this vector. Okay, that's that. Second vector, part B, we have 1/2. So the magnitude of this is going to be the square root of 1/2 squared plus 1/2 squared plus 1/2 squared plus 1/2 squared. And when we do that, we end up with the sum of 4 1/4, which add up to 4/4, which is 1. So the magnitude of that vector is 1. Which means when we go to find the unit vector, well, we've just determined that this already is a unit vector. So there really is no normalizing this vector. This vector is already normalized. It's already a unit vector. So we're just going to copy down the vector. And that's our answer. Okay, and for the last one, we have magnitude of, let's see, 1 squared, it's 3 squared, it's, 4 squared, 1 squared, and 3 squared. And if we add all that up, we have, this I think should be 36. So we end up with just a magnitude of 6, and so when we go to normalize this vector, we're going to have those original components just all divided by 6, and we can do some simplifying along the way. 3 over 6 is 1/2, 4 over 6 is 2/3, negative 1 over 6, and 3 over 6 is 1/2. And so there's our normalized vector for number 3 for part C. Okay, and then for number 3, we want to determine if this set of 3 vectors forms an orthogonal set. So we have, let's just write these down, we have 3, 3, 0, negative 1, 1, 4, and 2, negative 2, 1. Okay, so if they form an orthogonal set, all we have to check here is if the dot products between each combination of vectors is 0. And if they're all 0, then they're all orthogonal. So let's call these v1, v2, and v3. So the, let's see, dot product of v1 and v2 is going to be -3, so -3 plus 3 from the middle, and then there's 0 from the bottom, so this adds up to 0. Then if we do v1 with v3, here we get, that's 6 minus 6, and then 0 again on the bottom, 0 times 1, so that also comes out to be 0. So those are both of those pairs are orthogonal. The only pair we haven't checked is v2 with v3. And that's going to be -2, and then another -2, and then +4, which also comes out to be 0. So there we have 3 orthogonal vectors in a set, so this is an orthogonal set. Okay, next we have evaluate this orthogonal projection of u onto v. So we're projecting u onto v. Projecting u onto v, so we have to be careful about the way that we do this, the order that we get these in. U is 2, 1, 1, and v was 1, 4, 7. Okay, so doing this projection, let me just write out the formula. This is going to be u dot v over v dot v all times v. Remember, the vector we're projecting onto is kind of the focus of this formula, and it's going to be most of it. So u dot v, we have 2 plus 4 plus 7, 11, 12, 13 should be. So we get 13 on top. Let's just double check that. This is 2 plus 4 plus 7. Yeah, so that's 13. So then the dot product of v and v is going to be 1 plus 16 plus 49, which is going to be 66. So we have 13 over 66 times the v vector. And so this is our answer then. We have 1366 as the scaling factor that we're scaling all of these by. So if we do that, we have 13 over 66. 4 times 13 comes out to 52 over 66. And then 7 times 13 is 91. And that's over 66 also. So there is our projection of u onto v. Okay, and then number 5, we want to write this y vector as the sum of a vector in the subspace W, which is defined by this span here, and a vector in W perpendicular, and it's the orthogonal decomposition theorem we're using to do this. So to start here, vectors. We have our W subspace, which is the span of -1, 2, -1, and 3, 2, 1. And we have a y vector that is 3, 1, 3. So the idea is we're trying to find the closest vector to this y vector that we can in the subspace W. That's going to be the y hat vector. And then the other component that is not in W is going to be the z vector. And if we add those two together, we'll recover this original y vector. So to find the to find our y hat vector, the first thing we need to do is take the, we're using the orthogonal decomposition theorem. And this theorem requires that whatever vectors we're using as the basis to the subspace that we're using in this theorem, these vectors have to be orthogonal. So currently we have two orthogonal vectors. Let's check this. We have -1 times 3 is -3, 2 times 2 is 4, and -1 and 1 is -1. So this comes out to 0, the dot product between these. So these are orthogonal vectors. If these are not orthogonal vectors, we have to make sure that we have to make them into orthogonal vectors first. We use the Gram-Schmidt process, just one step of that, to make this second vector orthogonal to the first. So that's if we didn't already have two orthogonal vectors there to start out with. Okay, since this is an orthogonal basis, we just need to use this formula. Let me go over to the this first orthogonal decomposition theorem in our formula sheet and use that to make the y hat vector. So our y hat vector is going to be first the projection of y onto this first vector. Let's call this u1 and this will be u2. So the projection of y onto u1 means the dot product of y and u1, which is -3, 2 and -3, that's -6, and 2 is -4. And then the dot product of u1 with itself is going to be 1 plus 1 plus 4 is 6. So that times the u1 vector. And then another term for the u2 vector, so we take the dot product of y and u2. That's going to be 9, 11, and 3 makes 14, so it's 14 over the dot product of u2 with itself, which is 9 plus 4 is 13, plus 1 is 14, so 14 over 14 times the u2 vector. Okay, and if we only have two vectors, we only have these two terms, that should be it. So then we have, this is -2/3 times this vector. Let me just clean this up a little bit. And just 1 times this vector. So if we do this, -2/3 times -1 is 2/3, and 2/3 plus 3, so 2/3 plus 3, we could say is 2/3 plus 9/3, so that would be 11/3. Then we have here -4/3 plus 2. -4/3 plus 2 is -4/3 plus 6/3, so that would be 2/3. And then +2/3 plus 1 would be 1/3. Or no, rather, positive 2/3 plus 1 would be 5/3. Okay, so then once we have the y hat vector, so this is then the part of the y vector in W, or the closest vector to y in W. So once we have that y hat vector, the only other thing we need is the z vector, which is the other part of it that will add to y. So the z vector just comes from y minus y hat is our formula there. Y minus y hat. So that original y vector minus the y hat vector we just made. And if we do that, I'll save the calculations, just get from the answer sheet. we should have negative 2/3, 1/3, and 4/3. Okay, so if that's z, then these are our answers for the question. Our answers are the y-hat vector and the z vector. But we can now check that if we add these two vectors together, we will get our original y vector. All right. So next here we have number 6, use the Gram-Schmidt orthonormalization process to transform this basis into an orthonormal basis for R3. So we want to just use the process all the way through. And try to convert this basis. Let's copy this down. So we have 0, 1, 1, 1, 1, 0, and 1, 1, 1. And we're using the Gram-Schmidt process. So in the formulas that I give on the formula sheet, these three vectors in the original basis would be the x vectors, would be x1 through x3. So then our first step is to find these v vectors that are the orthogonal versions of our basis vectors. So v1 is just going to be equal to x1. Don't have to do anything there. v2 is going to be x2 minus the projection of x2 onto v1. So that looks like the dot product of x2 and v1, which is just 1, over the dot product of v1 with itself, which is 2. So we have 1/2 of the v1 vector. Okay, and then we'll calculate that in a minute. Let's also get v3. v3 is going to be the x3 vector, the third vector from our basis, minus the projection of x3 onto v1. So the dot product of x3 and v1 is 2, and the dot product of v1 with itself is 2, and then the v1 vector. And then we're also subtracting the projection of x3 onto v2. So actually, before we finish this, we need to finish and get v2. So v2 is, let's see, 1 minus 1/2 times 0 is just 1. 1 minus 1/2 times 1, so that's 1 minus 1/2 is 1/2. And then 0 minus 1/2. So there's our v2 vector. And now for v3, this last term is the dot product of x3 and v2. So these together is 1 plus 1/2 minus 1/2, so that just comes out to 1. That dot product comes out to 1. And then the dot product of v2 with itself, which is going to be 1 plus 1/4 plus 1/4. That's 1 plus 1/2, which is 3/2. Okay, times that v2 vector. So usually the best thing to do in this situation is just take the reciprocal of our fraction here. So if we have 1, 1, 1 minus, this is just 1, so we're just subtracting this vector, minus, then let's call this 2/3, 1, 1/2, negative 1/2. Okay, so now we just have to add all these together, and again, I'll save some of the work there and copy down our answer. So we have, for the last vector in the orthogonal basis, we have 1/3, negative 1/3, and positive 1/3. Okay, so the three vectors we found here form an orthogonal basis, so we could call this B prime. according to the formula. But they're not an orthonormal basis, and the question asked for an orthonormal basis. So the last thing to do would be to take each one of those vectors and normalize it. We'll call these u's. So u1 is v1 normalized. The magnitude of v1 is 2, so we want 1 over 2 times this vector, or divide the vector by 2. And that makes 0, 1 half, 1 half. Sorry, the magnitude, not the dot product anymore. Fix this. Okay, so the magnitude of v1 is the square root of 2. So we need the square root of 2 down here instead. So 1 over the square root of 2 times this vector. So that's 0, 1 over the square root of 2, 1 over the square root of 2. Okay, and then u2, we need to normalize v2. So we want to make sure we're looking at the actual last form of v2 and v3 and not the original vectors. So the magnitude of this is the square root of, let's see, 1 plus 1/4 plus 1/4. So I guess I already know that this is 3 halves, so we want the square root of 3 halves. And if this is the square root of 3 halves, and we're dividing by the square root of 3 halves, then that would be like multiplying by the square root of 2/3. So just to keep the fractions a little bit nicer, let's do that. And then multiply that by this vector here. So then, putting these together, I'll put it in the same form as I have on my answer sheet. The first one is just the square root of 2 over 3. I think I separated those on the answer sheet, but they don't need to be separated. It's just the square root of 2 over 3. And then in the middle we have the square root of 2/3 times 1/2. And one trick we can always do is, this is why it helps to separate these, is if I have the square root of 2 and I have 2, there are always 2 square roots of 2 hiding in this 2 here. So if I cancel this out, I cancel one of these and have 1 left over. So there's 1 over the square root of 3 and the square root of 2 now, which is the square root of 6. So we get 1 over the square root of 6, and then the last one is just negative 1 over the square root of 6. Okay, and then u3. We have our vector here. We want the magnitude of this v3. So that's square root of 1/9 plus 1/9 plus 1/9, which is the square root of 3/9, which is the square root of 1/3. So the square root of 1/3 is what we're dividing by. And again, if we just think about 1 over this, take the reciprocal, we have the square root of 3. So dividing by the square root of 1/3 is the same as multiplying by the square root of 3. And again, because we're multiplying the square root of 3 and there's a 3 on the bottom, we can cancel that out, and it just leaves a square root of 3 on the bottom of each of these. And that's it then. These 3 vectors that we got from normalizing our orthogonal vectors, these are now orthonormal. So an orthonormal basis would be the set of these 3 vectors. Okay. All right, next we have find a QR factorization for this matrix A. Let's go back, so number 7. We want a QR factorization for A equals negative 1, 3, 2, 1, 3, negative 2, 4, 0, 1. So for a QR factorization, the first step is to find Q. And Q has to be made of an orthonormal basis for the column space of A, the columns of A. Usually that just means take the columns of A and make them orthonormal. That's assuming none of them are dependent on each other, but actually if we just test that these are orthogonal, then we don't really have to test that they're independent. We'll look at that in a second. So if I just check if all these columns are orthogonal, these two together have a dot product of 0, because we just have these first two to add. These two together, this is 6 minus 6, also have a dot product of 0. And then those two together have -2, another -2, and a +4. That also makes 0. So we can find out that all three of these columns are already orthogonal to each other, which is almost good enough, but we need Q to be an orthonormal basis for A. So what I mentioned before was that if I check that these three vectors are orthogonal, which they are, to be orthogonal means that they have to be independent. And we had a theorem that said exactly that, that if you have a set of orthogonal vectors, they're automatically linearly independent. So we don't have to check that these actually form a basis, because if they're orthogonal, they have to. So anyway, to make Q, we need to normalize each of these vectors. So let's actually just jump straight to that. Let's make our Q matrix. We're normalizing these three vectors. So the magnitude of the first vector is the square root of 16 plus 1 plus 1 is 18. We can simplify this square root of 18 actually pretty well. Square root of 9 times the square root of 2. So let's just use 3 square roots of 2 for that. We could use the square root of 18. I'm not going to be picky about the form of our radicals, but let's use this. So divide each of these by 3 root 2. So -1 over 3 root 2, 1 over 3 root 2, and 4 over 3 root 2, which we could also probably simplify a little bit, but I'll just leave it like that. Then for the next one, second column, we have a magnitude of, let's see, 9 plus 9 is also 18. So again, 3 root 2. 3 divided by 3 root 2 is just 1 over root 2. And then again, 1 over root 2, and then we have a 0. And then for the last one, the last column has a magnitude of 4 plus 4 plus 1, that's 9. So this is actually a 3. So if we divide those components by 3, we have 2/3, -2/3, and 1/3. And that's the Q matrix. So again, all we have to do for the Q matrix is check that these columns are independent. If they are, then we just have to normalize them and we get Q. If they're not, then, well, the next problem has a set of vectors that are not orthogonal, and we'll see what happens there. Then the last step to this is we need to find the R matrix to finish the QR factorization, and we'll use this formula for the R matrix. So we need to take the transpose of this Q matrix we just made. And multiply that by the A matrix. 1, 3, 2, 1, 3, -2. Just like that. Multiply these matrices together, and we'll have our answer. And I'm going to skip the steps to this. But if we multiply these matrices together, we should end up with 3 root 2, 0, 0, 0, 3 root 2, 0, and 0, 0, 3. Let's confirm, let's say just this first component. So take this times -1 is going to be positive 1 over 3 root 2. And then again, same thing, 1 over 3 root 2. And then we take this last component times 4, and that's 16 plus 16 over 3 root 2. So that's 18 over 3 root 2. Whoops. 18 over 3 root 2. And we want to get down to this, so if we do some simplifying first, cancel a 3 out of this, and we get, what is that? Is it 6? Yeah, it is 6. Okay, that's what I thought. 6 over the square root of 2. And the other thing we can do is remember that 6 has a factor of 2 in it, so we can use this trick again of canceling the square root of 2 out of the 2, and it leaves another factor. And that's where we get 3 times the square root of 2. Okay. Then next we'll do number 8. So same idea, find a QR factorization for this matrix. This time we have A equals 1, 1, 0, 1, 1, 2, 1, 0 down the columns. Okay, so again, for a Q matrix, we just need the normalized vectors of an orthogonal basis. So again, we have to check to begin with here if these vectors are orthogonal. And in this case, they're not, because the dot product here would be 1 plus 2, so that would be 3. So these are not orthogonal vectors. So the first step is going to be to make them orthogonal, and then we can normalize them and do all the other stuff we need to do. So to make these orthogonal, the way that we have of making vectors orthogonal to each other is with the Gram-Schmidt or the normalization process. We don't have to do the entire process. We can just make the vectors orthogonal. So that's what we'll do. This is x1, and this is x2. And v1 from the Gram-Schmidt process would be just the same as x1. And v2 is going to be x2 minus the projection of mixing up the order here, of x2 onto v1. Yeah, so of the original vector here onto this v1 vector. So the dot product first of x2 and v1 is 1 plus 2, I think that's it, so that's 3. And then the dot product of, it would be v1 with itself over here, so this would be a 3 also, times the vector v1. Okay, so this is just 1, so we're essentially just subtracting these vectors, and if we do that, 1 minus 1 is 0, 2 minus 1 is 1, 1 minus 0 is 1, 0 minus 1 is negative 1. Okay, so now we have 2 orthogonal vectors, and we're trying to find the QR factorization. So now that I have a set of 2 orthogonal vectors, and because these vectors came from the original vectors in A, they still form a basis for the same subspace that these columns formed for the column space of A. So we can use these as our columns in Q. The only thing we have to do is normalize them first. So the magnitude of both of these is the square root of 3. So when we make the Q matrix, we're going to take these 2 columns, but just divide them by the square root of 3. So we get 1 over root 3, 1 over root 3, 0, and 1 over root 3. And then for v2, we get 0, 1 over root 3, 1 over root 3, and negative 1 over root 3. And then to find r, all we need to do is take again by our formula Q transpose A. And so Q transpose, we lay this sideways, we have 1 over 3, 1 over 3, 0, 0, 1 over root 3, and negative 1 over root 3, times the A matrix. Okay, and this should be pretty quick because we are just going to end up with a 2 by 2 matrix. So first, here we just have the sum of all three of these. We're going to get 3 over root 3 in this first component. So 3 over root 3, we can simplify to square root of 3 by using that cancellation trick. Second, we'll do the first row in the second column here, and we'll have 1 plus 2 of these. So again, we have 3 root 3, so that's the same thing, or 3 divided by root 3, which is root 3. Now, the second row in the first column, we have 1 over root 3 minus 1 over root 3, which gives us a 0. Remember, R is always supposed to be upper triangular, so we're expecting to get a 0 down there. And then the last component is going to be 2 over root 3 plus 1 over root 3, so again, root 3. All right, and then next, number 9, we want to determine whether each of these matrices is symmetric. And we can just look at these here. So this matrix, part A, we could tell right away is not symmetric because what we're looking for is that, well, to be symmetric, this matrix has to be equal to its own transpose. So we could take the transpose of the matrix and then just compare them. But we can also remember that in taking the transpose, what essentially happens is these elements across the diagonal switch places. So the 2 and the negative 2 here would end up switching, and the 2's on the corners would end up switching, and then these 2's on this other sort of diagonal would end up switching. And if that happens, we don't have the same matrix. Or in other words, the 2 in this top middle component and the negative 2 in this left middle component are not the same, and so this isn't a symmetric matrix. So for part A, the answer is no, this is not symmetric. Next, if we carefully look at all of these sort of diagonals, the negative 1's match here. On this next diagonal, the 5's match across the middle. Remember, it doesn't matter what the actual middle components are because they're not reflected onto anything. So the 5's here need to match. And then we have 2 4's here that match, and then 2 negative 2's on the outside, and the 6's across here match, and the negative 2's here match also. So everything seems to be symmetric, everything seems to match, and so part B is a symmetric matrix. And again, if it's easier, if you just write out the transpose, just sort of row by row, and then compare them directly, that will work too. And part C, has some symmetry. I mean, these 2's kind of reflect each other, the 3's do. But the thing that we want to notice with C right away is that it's not a square matrix. Whereas this is a 3 by 3, this is a 4 by 4, this is a 2 by 3 matrix, and a non-square matrix can never be symmetric. Just by definition of being symmetric means that C is equal to its own transpose, but the transpose of this is a completely different size, and so it can never be equal. So part C, the answer here is also this is not a symmetric matrix. So the only symmetric matrix here is part B. All right, so next we have number 10, find a least squares solution for the inconsistent system AX equals B, given these two, A and B. We assume that this is an inconsistent system when we find this least squares solution, because if it's a consistent system, then it has an actual solution, and there's really no sense in finding a least squares solution. So this is just kind of a given. The least squares solution given A and B. So let's start with our A matrix is 1, 2, negative 1, 3, 2, negative 2, and 0, negative 3. And our B vector is 1, negative 6, 8, 3. Okay, so for the least squares problems, we have this set of normal equations, which is mainly what we're going to use for this, which says A transpose A times X equals A transpose B. We can kind of think of these as grouped together. A transpose A is going to be just a single matrix, and that's like our coefficient matrix in this equation, and then these over here are going to multiply to make a single matrix, and this is like our constant sort of constant vector on the other side of this equation. So the general form of this equation is still AX equals B. It's just that we're using this matrix to represent the coefficient matrix. We're using this vector to represent the other side of the equation. All right, so we'll want to start here by finding each of these matrices. So we have A transpose A is going to be, let's see, A transpose, negative 1, 2, 0, 2, 3, negative 2, negative 3, times A. And then we also want A transpose times B. B is going to be this A transpose matrix times our B vector, like that. Okay, so A transpose A, do this first. Let's see, this first matrix is 2 by 4, and this is a 4 by 2. So we should end up with just a little 2 by 2 matrix here. So first we're going to have 1, let's see, 1 plus 1 plus 4 there is going to make 6. And then we'll have, let's see, this row in this column is going to be 2, minus 3 is negative 1, minus 4 is negative 5 there. And then down here we're going to have 2, minus 3 is, let's see, double check that, 2 minus 3 is negative 1, and then minus 4 is negative 5. So there's another negative 5, and then the last component here is going to be 4 plus 3 plus 9 is 13, plus another 4, 17, and then plus 9 again, should be 26. So there's our A transpose A matrix. And now to multiply these to get A transpose B, we're going to have 1 plus 6 is 7, plus 16 would be 23. And then we have 2 minus 18. Let's just get this all together. Let's see, we have 2 minus 18 minus 16 minus 9. So this should come out to negative 41. Okay, so we have our A transpose A, we have our A transpose B. So now the system that we're actually trying to solve, now that we've found these matrices, we have the A transpose A matrix times our X variables times equals the constant matrix over here. And we're solving this system, and again, this is just like an AX equals B kind of system. It's just that the A and the B matrices that we're using in this system come from the normal equations, come from these products. So if we want to solve this system, we can solve it like any system. We have a couple different methods. we could put this together in a augmented matrix would probably be the standard way to do it. So make an augmented matrix out of everything, and then put this in row echelon form, and we get our solutions from there. That would be fine. I'm going to use the other method, or another method we could use, which is if I have ax equals b, if I want to solve the equation ax equals b, we can use the inverse. If I multiply both sides of this by the inverse of a, we end up with x is a inverse b. So if I want to find x, if I can take the inverse of a, then I can just do a inverse times b. And since a is only a 2 by 2 matrix, the inverse shouldn't be too bad. So let's do that. Find a inverse, which is, let's see, the matrix itself is going to end up, we're going to swap these, and then we're going to change the sign, so these will both be positive 5. And then we divide by the determinant. So the determinant here is, let's see, 6 times 26 minus negative 5 times negative 5. That is 131. So we're dividing all these numbers by 131. Now, rather than actually dividing them right now by 131, I'm going to go ahead and set this up. So we're finding x, which is a inverse times b. So we have our a inverse, which is I'm just going to keep in this form with the constant on the outside, times b, which is our 23 negative 41 vector. And I'm not referring to the b in our original problem, but the b in this kind of, now that we've gotten this down to just an equation of matrices, this is acting like our b matrix, our constant vector anyway. And then let's multiply these matrices together first, and then we'll multiply the constant in, and the hope is that multiplying these matrices together will give us some numbers that will make the fraction here come out a little bit easier. So we're going to have 1 over 131 times the product of these two matrices, which first we have 26 times 23 minus 41 times 5. That is 393. And then we have 5 times 23 minus 41 times 6. That is negative 131. So then finally we end up with dividing things by 131. You can check that 131 goes into 393 3 times, and then of course goes into that negative 1 time. So that's our solution then. 3, negative 1 is the solution to this system, which, because it's still the same x vector, is the solution to this normal equation system that we had over here, which was the least squares solution to this problem. So again, what we did with this one was make the normal equations, make A transpose A and A transpose B, find those two matrices, and then put them together in a system, and then we could either solve that system using our augmented matrix, putting it in row echelon form, etc. We should come up with the same solutions, or we can use the inverse matrix to do it. Okay. So then let's look at number 11, which says, suppose a matrix A has eigenvalues 1 and 3, and eigenspaces S1 equals this span and S3 equals this span. Find the orthogonal matrix P, which orthogonally diagonalizes A. So the key to this problem is we don't really need to do that much. We don't actually know what this matrix A is. I'm not giving you a matrix. I'm just giving you the eigenvalues that some matrix has, and then the eigenspaces that it has. So we already have all that work done. Remember, if we want to find the P matrix, if we want to diagonalize a matrix, we need the eigenvectors first. So we already have those. So all we really need to do is put these eigenvectors together. We have 3 eigenvectors right here. 2 that come from the 2-dimensional subspace for this first eigenvalue, and then the 1 from this other eigenspace. We could put all 3 of those vectors, and let's just do this real quick. We can put all 3 of these vectors in a matrix. So we have 1, 2, 0, negative 1, 1, 0, and 0, 0, 1. But the problem with this matrix is it diagonalizes A, but it doesn't necessarily orthogonally diagonalize A. To orthogonally diagonalize A, these 3 vectors need to all be orthogonal, or this needs to be an orthogonal matrix. But if we look at this, this is not an orthogonal matrix. If we take the dot product of these first 2 vectors, we have negative 1 plus 2 is 1, so they're not orthogonal. So the thing to recognize when we look at this is we're given these eigenspaces. We had some theorems that told us basically that if you take an eigenvector from one eigenspace and an eigenvector from a different eigenspace, that those will be orthogonal to each other. And that's true. If we check 1, 2, 0 is orthogonal to 0, 0, 1, and so is this vector. So the only vectors that are a problem are these 2 vectors in the same set, because if we have 2 vectors that make an eigenspace, that sort of make a basis for our eigenspace, they don't necessarily have to be orthogonal. And the ones I've given to you aren't. So what we want to do for this problem is first make sure we have 3 orthogonal vectors, and all that takes in this case is just making these 2 orthogonal to each other. And the way that we make 2 vectors orthogonal to each other is using at least part of the Gram-Schmidt process. So let's just do that now. So we have v1 is going to be the original first vector, is going to be x1, and then v2 is going to be x2 minus the projection of x2 onto v1. So x2 dotted with v1, take this dot product, we have minus 1 plus 2, we already saw that before, that was 1. And then the dot product of v1 with itself, which is 5, times the v1 vector. Okay, so that's going to give us negative 1 minus 1/5. It's negative 6/5. 1 minus 2/5 is 3/5. And then 0 minus 1/5 times 0, well, it's going to stay 0. Okay, so now these 2 vectors should be orthogonal to each other. We can check. And they should still both be orthogonal to this other vector, the third vector we had from the different eigenspace. So now we have an orthogonal matrix we can make. So P is the original first vector and the, we can say, orthogonalized second vector. So these are both from the first eigenspace, but now they're orthogonal. And then the vector from the other eigenspace, which is still orthogonal with both of the original ones. This will make our P matrix. And that's all we have to do for this problem. It says we want to find the P matrix which orthogonally diagonalizes A, as long as we have a matrix that is made of the eigenvectors of the matrix A that are also all orthogonal to each other, then that is the matrix that we want. All right, and the last problem we'll do is number 12. We want to do the same thing, find an orthogonal matrix which orthogonally diagonalizes A. We have this 2 by 2 matrix to start with. Okay, so we're using A equals 2, 6, 6, and 7. And we want to find this matrix P. So again, well, I guess in this case we have a little bit more work to do at the beginning because we need the eigenvectors of A in order to make the P matrix. So to get the eigenvectors of A, we want the determinant of lambda I minus A. So here that's going to be lambda minus 2, negative 6, negative 6, lambda minus 7. Take the determinant of that, and we have lambda minus 2 times lambda minus 7 minus, this would be 36. And as we start to simplify this, it's 14 minus 36, lambda squared, 14 minus 36 is negative 22. And then we should see this should be factorable here. I did change this problem a little bit from the one that was originally on the review sheet, which turned out not to be factorable. I must have made some mistake coming up with it. So this one with 7 in the bottom corner should be factorable. So the factors here are going to be lambda, I think we'll want minus 11 and plus 2. That makes negative 22, and it also makes the negative 9. So we have eigenvalues of 11 and negative 2. So now we want to find the eigenvectors that go along with these eigenvalues. So first of all, we have, let's see, we have lambda equals 11. So plugging 11 into our lambda I minus A matrix here, we have 9, negative 6, negative 6, and this would be 4. If we start reducing this, I can take a factor of, let's see, a factor of 3 out of both of these first two. So we'll divide the top row by 3, and we get 3, negative 2. And if I divide the bottom row by 2, we'll get negative 3 and 2. And then we see that the two rows are actually multiples of each other, and if we just subtract them, we can cancel out that bottom row. We get this. So this tells us 3x1 minus 2x2 equals 0. And bottom equation gives us nothing. And so we can use this to parameterize our solutions. 3x1 equals 2x2. So let's say I let x2 be t. Let me double check. I want to do it. Yeah, I did it both ways in the answer sheet, so we can do it either way. So if I let x2 be t, then this gives me x1 equals negative, no, it'd be positive 2/3 x2. 2/3 x2. So this is 2/3 of x2, which is t. And then we have t times the vector 2/3 1, which is the vector 2/3 1, will be a basis for that eigenspace. And then we'll do the same thing again with lambda equals negative 2. In our matrix up here, that's going to make, let's see, plug in negative 2, we have negative 4, negative 6, negative 6, and negative 9. And we have basically the same situation here. If we divide these by 2 and by 3, the two different rows, we'll have negative 2, negative 3, and negative 2, negative 3. So we can get rid of one of those And let's also just divide the top row by -1 to make that easier. And we have this matrix. So this gives us 2x1 plus 3x2 equals 0. So that means x1 equals -2/3. No, this one will be dividing by the 2. -3/2 x2. So that's going to be, if x2 is t, x1 is -3/2 t, which we can write t times -3/2 1, or the -3/2 1 can be our basis for the second eigenspace. So now we have the basis of each of these eigenspaces. And again, what we're trying to do here is find a matrix P that orthogonally diagonalizes this matrix. One thing that we could have noticed at the start is that this is a symmetric matrix. And we have a theorem that says a matrix is orthogonally diagonalizable if and only if it's a square matrix, if it's a symmetric matrix. So this has to be a symmetric matrix to begin with for us to be able to do this. But also, if this is a symmetric matrix, then we know that this is possible, and generally when we do this process, the vectors that we get here should be orthogonal. It is possible that, like in the last problem, maybe if we have a space that has multiple vectors in a single eigenspace, we might have to make them orthogonal using the Gram-Schmidt process. But in this case, we have two different sets. These should automatically be orthogonal to each other. We can check, but if you take 2, 3, 2/3 and 1, and -3/2 and 1, multiply these together, and we'll actually have -1, and then on the bottom we have +1, and so these are orthogonal. So that's all we need for P then. The P matrix is those two orthogonal rows that come from the eigenspaces of A. And I put two different versions of the answer on the answer sheet because when we made our parameterizations here, another thing we could have done was let x1 equal t and then let x2 equal whatever it equals. And then we essentially kind of end up swapping these. But either way is valid. There are different matrices we could come up with, but this is one of our potential P matrices that diagonalizes the matrix.